So diffusion, the phenomenon of material transport by atomic motion. Here I'm going to show copper, and I'm going to diagram the atoms inside of the pure sample of copper. Right next to it I will draw a sample of nickel, and I'll do the same with nickel. Now over time, with these two samples sitting next to each other, there will be diffusion, the copper into the nickel into the copper, until we have a complete mixture of both. So right here I draw the copper going from 0 to 100 and the nickel from 0 to 100. Now over time, the copper will go into the nickel into the copper, and we'll end up with a complete diffusion of copper into nickel. Now here I will show, as the position changes, the concentration of copper into nickel looks like that, and the concentration of nickel into copper looks like this. So we have our 100% here and 0% here. I've written time, but that's really concentration. Next, we're going to show some diagrams of diffusion, some mechanisms of diffusion. First, I'm going to diagram vacancy diffusion. Now these boxes here that I'm drawing, those are vacancies, and we're going to see the impurity atom moving from vacancy to vacancy, vacancy diffusion. So when an impurity atom moves from vacancy to vacancy, it strains the lattice. And so this one, it induces a lot of lattice strains because the molecules are large and they're moving from each vacant site. Now the requirement is that there has to be a vacant site next to it that is open. Next, we're going to show interstitial diffusion, so I'm going to draw the same lattice, but now remember our interstitials are really small, and those move from interstitial site to interstitial site. This is interstitial diffusion. So the reason that interstitial diffusion happens so much more quickly than vacancy diffusion is that the lattice strains induced by this little interstitial impurity is a lot smaller than the lattice strains induced by the vacancy diffusion. Those molecules are a lot bigger, so to get from site to site, it'll incur a lot more lattice strain, which has to do with the activation energy, which we're going to talk about next. So the process whereby atoms of one metal diffuse into another is called interdiffusion, also termed impurity diffusion. The next one that we talked about was self-diffusion, and self-diffusion is where atoms are all of one type and they exchange positions inside. So I mentioned activation energy. Here we're going to draw a graph of the activation energy, and I put a little bump here for a reason. That's the amount of energy required to strain the lattice so that we can actually have those atoms moving from vacancy to vacancy or from interstitial to interstitial. That bump will be a lot smaller for the interstitial diffusion, a lot bigger for the vacancy diffusion. We will denote that QD in the equations to come. So, in the book, we are given, as an example, we are given the plot of the logarithm of the diffusion coefficient versus the reciprocal of absolute temperature for the diffusion of copper in gold. That's what this line here represents, so we're going to find a way to make it linear. Now, the 1.1 and the 0.8 that I've drawn on the graph, those are points given to us by in the book, and along this line. On the other side here, I'm drawing a logarithmic representation of the diffusion coefficient in meters squared per second. Now down here, oops, let's see if I'll catch my mistake. There we go. That is the diffusion coefficient up there on the top, and then our reciprocal temperature down at the bottom in Kelvin, in absolute Kelvin. Yeah. Okay, so the equation given is diffusion equals dO, which is our pre-exponential, times e to the negative qd over RT. So d is the value for the diffusion that we're going to get. dO is our pre-exponential. qd is the activation energy that we talked about before, and then R, our constant R that we're familiar with, and T is the reciprocal temperature, again in Kelvin. So the slope of this line, we want to try to make it linear. We know that's going to be QD over 2.3 R. Now the reason that it's 2.3 R is that it's a logarithmic function. If it was a natural log, it would just be R actually. Now remember our equation for diffusion right here, written it exactly like we talked about before. If I take the log base 10 of both sides, then we end up with log d and the log of the pre-exponential plus the log and the e to the cancel out, and so we are left with qd over 2.3r, like we talked about before, times the reciprocal temperature. Now we want to make it look linear, y equals mx plus b. So we know that the 1 over t, that's going to be our x. That's going to be what we vary. The qd over 2.3r, well, that's our slope. And then the log do, that is going to be our y-intercept. So now we have a linear equation. So from our linear equation, we know that the slope is equal to the negative qd over 2.3r. Now, we know that the QD is our activation energy. We can solve for QD by saying the slope is the change in y over change in x. So here I'm just algebraically solving for QD using what we know a slope is. So the change in y is going to be the log d1 minus log d2, and then the change in x is going to be the difference in our reciprocal temperatures. Now we got those from our graph. Here I drew lines down and we chose 0.8 and 1.1 arbitrarily, but those are good places, nice even numbers. Now up at the top we're estimating over, so we're drawing a line over to our y-axis to estimate what diffusion coefficient that is. Now we estimated 12.4 and 15.45. Now note that that is a logarithmic scale, so this is 10 to the negative 12.4, 10 to the negative 15.45. So next we're going to start plugging in some values. So QD is negative 2.3 R times, now we're going to do the slope, the change in y over the change in x. So the change in y is going to be log d1 minus log d2 over the change in the reciprocal temperatures, or the change in x. So now remember that slope is change in y over change in x, so we're going to go back to our graph and look at those values in just a second. So QD, negative 2.3R, now we'll insert our own values of 12.4, negative 12.4 and a negative 15.45, subtracting those, and then we are going to subtract our first inverse temperature from our second inverse temperature, so we have there Kelvin to the negative 1. Now the 10.3 will, or 10 to the negative third, we'll get to that. Plugging that into my calculator, I get 194,000 joules per mole. So we can say that is 194 kilojoules per mole. And we'll just leave it at that. Now the 0.8 times 10 to the negative third, that reciprocal temperature, that is determined because we are told from our problem that our temperatures are given in 1,000 over K. So that's where we got our 10 to the negative third there when we solved the problem. Alright, so now that we have QD, we can go back and solve for our pre-exponential, or D sub O. Now that we've found our activation energy, we can go back and solve for our diffusion coefficient, the pre-exponential. So now we can just remember we started with this equation, log D equals log D sub O plus QD over 2.3R times the inverse temperature. So we need to solve for log DO, so we're just going to rearrange this algebraically. We end up with log D sub O equals log D plus QD over 2.3R times our inverse temperature. Now, we're just going to plug in the activation energy that we've already solved for, the 194,000 joules per mole. I've arbitrarily chosen our second set of data points to use in calculating and solving for D sub O, so I use negative 15.45 and 1.1 times 10 to the negative third Kelvin. So now just plugging that into the calculator, not forgetting to divide by 2.3 times our value for R, the constant 8.31 joules per mole K. So we solve for our diffusion, our pre-exponential, and we get 10 to the negative 4.28 meters squared per second. Now the value that my calculator spit out at me was negative 4.28. So we end up with a pre-exponential of 5.2 times 10 to the negative fifth meters squared per second and an activation energy, which we already solved for. Now we have to remember that the d sub o, that was the log of the pre-exponential, so we need to do 10 raised to the power of negative 4.28, and that's how I did that last little bit there. And so now we have solved for both the pre-exponential and the activation energy.
Now I want to start off with steady state diffusion. I'm not going to go into too much detail about it, but I will mention that steady state diffusion, the diffusion flux does not change with time. What is the diffusion flux, you might ask? Well, the diffusion flux is how fast diffusion occurs, or the rate of mass transfer. Now there's actually an equation to calculate the diffusion flux. It is J equals m over AT. M is the mass, A is the area across which diffusion is occurring, and T is the elapsed diffusion time. Now, last thing I want to mention is concentration gradient. Concentration gradient is related to the concentration profile, except the concentration gradient is the slope at a particular point on a curve of the concentration versus position graph, which I will show you here in just 1 second. So the graph is the concentration versus position, and as you can see there's two concentrations, C sub A, C sub B, in two positions, X sub A, X sub B. So the concentration gradient is a slope of this graph, where it's the delta C over delta X, because we know the slope is rise over run, which is also C sub A minus C sub B over X sub A minus X sub B. Now we are going to discuss the non-steady state diffusion. As you can tell, the non-steady state diffusion is going to differ from the steady state diffusion. If you recall the steady state diffusion, the diffusion flux and concentration gradient were both fixed or looked at as constants, while in the non-steady state diffusion, the diffusion flux and concentration gradient at some particular point in a solid vary with time. This just means as time goes on, the diffusion flux and concentration gradient will change. Now, this is going to lead us to Fick's second law, because these two conditions are changing. Fick's first law is no longer convenient to use. So in order to find Fick's second law, what we do is we take the partial derivatives, and what we end up with is a partial derivative of the concentration over the partial derivative of time. And we set that equal to the partial d as the diffusion coefficient times the second partial derivative of concentration over the partial derivative of x, being the position after a certain time, squared. Now, after giving the variables of Fick's second law some boundaries, what we end up getting is our error function formula, where it's C sub x minus C sub o over C sub s minus C sub o, set that equal to 1 minus the error function of x over 2 times the square root of dt, where d is the diffusion coefficient, t is time, and x is a certain depth, at a certain depth. Now, you may be wondering what these variables stand for. Well, C sub x is a concentration at a certain depth at a particular time, t. This makes sense because x stands for our depth or position, where C sub x is our concentration at that depth or position. Now, C sub o is the initial concentration of the solution. Now, the boundaries for that is before any diffusion, any of the diffusing solute atoms in the solid are uniformly distributed with concentration of C sub O. What we've seen normally in our equations and our assignments and problems that we've had to work through is unless it is otherwise specified, our C sub O is normally 0. And that makes sense because our initial concentration, unless diffusion has already occurred, is going to be 0. This leads me to our last variable to define, and this is the C sub s, where that is the concentration on the surface of the solid. The last part of this formula I want to specify is the error function of x over 2 times the square root of dt. This is the Gaussian error function. What it is the measurement of theory using probability and statistics. It's a very good estimation at a particular value. Now, to further define this function, although I've defined it pretty well, what it does is it shows the relationship between concentration, position, and time. And I'm going to show you this by drawing the graph that kind of just shows how everything correlates with each other. So what this graph is going to show is all of our variables that were in that error function. We're going to see that our C of O and our C of X. Now our x-axis is going to be our distance from the interface, x. Also, our y-axis is going to be the concentration. Now, as you can see, the distance from the interface, when x is 0, we are at the interface, and that's our concentration on the surface. If we bring that line out and we compare the two values, what we get is C of S minus C of O. That is our denominator. Now, we can see that the C of X minus C of O, our numerator, is further on to the left, but we can also see that it's at a certain distance, x, from the interface, we have another different concentration. We're going to look at an example problem now, anyways, right out of the Callister textbook. And what it is it says, consider one such alloy that initially has a uniform carbon concentration of 0.25 weight% and is to be treated at 950 degrees Celsius. If the concentration of the carbon at the surface is suddenly brought to and maintained at 1.20 weight%, how long will it take to achieve a carbon content of 0.8 weight% at a position 0.5 millimeters from the surface? The diffusion coefficient for carbon and iron at this temperature is 1.6 times 10 to the negative 11th meters squared per second. Assume that the still piece is semi-infinite. Now, picking out details from that story, what it is we're trying to find at what time is the surface concentration going to be 1.2%, where the initial concentration is 0.25 weight%, and the depth concentration is 0.8 weight% at a certain depth of 0.5 millimeters. So we'll give our variables some values where initial is 0.25 weight%, surface concentration of 1.2, depth concentration is 0.8, and x, the depth that we wanted at, is 0.5 millimeters, which is 0.5 times 10 to the negative third meters. Our d for diffusion value is 1.6 times 10 to the negative 11th meters squared per second. Now we know that we have that change x into meters because our the units for d include meters, and we want all of this to cancel out, so what we're left with in the end is seconds. So what I'm filling in the formula, the error function formula that I've shown you numerous times now, and I'm going to show you how to calculate and solve how long it's going to take for this diffusion with these specified concentrations that we want, how long that's going to take. So solving on the left hand side, what we get is 0.5789 equals 1 minus the error function of that. Now what we want to do is set the error function equal to a certain value. So solving for the error function, we find that it equals roughly 0.4211. Now going on from here, we're going to see this is going to lead to our extrapolation. Now what is extrapolating? I didn't know until earlier on in this course, but finding the definition on Google, Wikipedia to be exact, extrapolation is the estimation of a value based on a known sequence of values or facts behind the area that is currently known. Now we know that the error function is measurement theory using probability and statistics. So what this is basically saying is we have a bunch of known values at a certain z, which you'll see here in just a second. And with these and our values that we end up calculating, we're going to be able to find a probability, or we're going to be able to find a close enough value that we're going to be able to use to calculate this time that this problem is asking for. So what this table is right here is a quick demonstration of what the accepted values are, or known values are. Now when extrapolating, what we're going to do is set x over 2 times the square root of dt, and we're going to replace that with z, and this is going to come very handy here in just a little bit, you'll see. So earlier on we found the error function and what that was equal to. We replaced the x over 2 times the square root of dt with z. I told you it'd come in handy. And so what we do is we make a new table with our z and our error functions of z. So now we have our value of error function of z. So what we do is we find the points that it's closest to, what 2 points it lies in between, and then we leave our z as variable z, and we set it in between the two z values in our error function in between the two error function z values. So to write out this formula, what we do is z minus the lower bound z over the highest bound z minus the lowest bound z. As you can see how that relates to each other. We set that one equal to the r value of z, of error function z, minus the lower value of error function c over the higher value of error function z over the lower value error function c. You can see how these all relate to one another. So this is how the equation looks like without any of those arrows or anything pointing anything out. Now you can see how they relate to one another, how it's the upper bound minus the lower bound in the denominator and r value minus the lower bound in the numerator. After we have all of that written up, what we do is we solve for z. We solve for z because we already have our error function at z, and so the only variable that is left is our z. That is the equation that was just shown earlier, just without the arrows this time. And what we do is I solve on the right hand side first, and what I do is I get a value of 0.851 roughly. Now I get rid of the denominator by multiplying it by both sides. What I get is 0.0426. So this means that z equals 0.392. Now, because z equals x over 2 times the square root of dt, I told you this would come in handy, what we can do is set them equal to each other, and having this, now we can solve for our t, our time t. So what we do is we get rid of the x on the other side, and we get rid of the 2 in the denominator. And we set that equal to 1 over the square root of dt, which is 1.6 times 10 to the negative 11th meters squared per second times time. So solving the left hand side, we get 6.377 times 10 to the negative 4th meters, and we set that equal to 4 times 10 to the negative 6th meters per square root of seconds times the square root of t. Solving for t, we get the square root of t equals 159.44 per square root of seconds. Now squaring both sides, we see that t equals 25,400 seconds, which is roughly 7.1 hours. I noticed when I wrote this, I made a mistake. It should be 25,400. I add an extra O on accident. But what this is this is a way to solve how long it's going to take for giving, when they gave us a certain concentration of surface, concentration at a certain depth, and whatnot, and this gives us how long that takes for the diffusion to reach that certain point. But remember, this is only for non-steady state diffusion.